Imagine floating through space far away from every star you have ever seen. No sunlight, no warmth, no glowing sky, just endless darkness. Now imagine a planet out there, drifting silently through that darkness. No sun to rise in the morning, no seasons, no day or night, just a world completely alone. Here is the question that sounds impossible at first. What if a planet can exist without a star? When most of us think about planets, we picture a simple idea: a bright star at the center and planets moving in neat paths around it. That is how we learned about the universe. Mercury, Venus, Earth, Mars, all of them depend on the sun. Without it, they would be frozen, lifeless rocks. So it feels natural to believe that planets need stars, just like plants need sunlight or fire needs fuel. For a long time, scientists believed the same thing. Stars were seen as the parents of planets. No star meant no planet. The idea of a planet without a star sounded like science fiction. A lonely world, lost in space, with no light to guide it. It felt too strange to be real. But the universe has a habit of breaking our expectations. Over the last few decades, astronomers have discovered something shocking. There are planets that do not belong to any star at all. They wander through space on their own, like cosmic orphans. These worlds are real. They are not rare accidents. In fact, there may be billions of them in our galaxy alone. These planets are called rogue planets, or free-floating planets. They do not orbit a sun. They do not shine by reflected starlight. Many of them are colder than anything we can imagine. Some are larger than Jupiter, some may be rocky like Earth, and some may hide secrets beneath thick layers of ice. How do we know they exist if they give off almost no light? How were they formed? Were they born alone, or were they stolen away from their stars long ago? And most importantly, could something be alive on a planet that never sees a sunrise? In this video, we are going to explore one of the most mysterious ideas in modern astronomy. We will travel to worlds that drift in silence. We will look at frozen planets wandering through the galaxy. We will uncover how scientists find planets that are almost invisible. And we will ask a question that changes how we think about life itself. Because even in the coldest darkness of space, the universe may still be full of worlds. Worlds without stars. Worlds without light. And perhaps worlds that are not as lifeless as we once believed. Before we can answer whether planets can exist without stars, we need to slow down and ask a very basic question. What exactly is a planet? It sounds simple, but the answer is more important than it seems. The entire mystery of starless planets begins right here. Most of us grow up with a clear picture in our minds. A planet is a round object that moves around a star. Earth goes around the sun, Mars goes around the sun, Jupiter goes around the sun. This idea feels so natural that we rarely question it. But science does not work on feelings, it works on definitions. In simple terms, a planet is a large object in space that is held together by its own gravity, is round in shape, and is not massive enough to produce its own light like a star. That is the basic idea. A planet shines only because it reflects light from somewhere else. It does not create energy by nuclear reactions in its core. This one detail already tells us something important. A planet does not need to make light. It does not need to burn. It only needs enough mass for gravity to shape it into a sphere. Gravity is the key player here. When an object in space becomes large enough, gravity pulls material inward from all directions. Sharp edges disappear. Over time, the object becomes round. That round shape is one of the strongest signs that we are looking at a planet, or something very close to one. Now let us separate planets from the other objects we find in space, because the universe is full of things that can look similar at first. A star is very different from a planet. Stars are giant balls of gas, mostly hydrogen, that are so massive and hot that nuclear fusion begins in their cores. Fusion is the process that turns hydrogen into helium and releases enormous amounts of energy. That energy is what makes stars shine. The sun is not just a bright object. It is a powerful nuclear furnace. Planets simply do not have enough mass to do this. Even the largest planets, like Jupiter, fall far short of what is needed to ignite fusion. Between stars and planets, there is a strange category called brown dwarfs. These are often called failed stars. They are larger than planets, but smaller than true stars. They can briefly burn a form of hydrogen called deuterium, but they never become real stars. Brown dwarfs blur the line and show us that nature does not always care about neat labels. An asteroid is much smaller than a planet. Asteroids are rocky or metallic objects that never became large enough for gravity to shape them into spheres. They are irregular, jagged, and uneven. Many asteroids are leftovers from the early days of planet formation. They are building blocks that never finished becoming planets. A moon, on the other hand, is an object that orbits a planet instead of a star. Our moon goes around Earth. Jupiter has dozens of moons. Some moons are surprisingly large and complex. In fact, some moons, like Europa and Titan, are bigger than the planet Mercury. Size alone does not decide what something is. Orbit does. This brings us to an important point. For a long time, scientists defined a planet mostly by what it orbits. If it went around a star, it could be called a planet. If it went around a planet, it was called a moon. This seemed logical, but it also created problems. In 2006, astronomers famously reclassified Pluto. Pluto was no longer called a planet because it had not cleared its orbit of other debris. This decision caused a lot of debate, but it revealed something deeper. Our definitions were shaped by our own solar system, not by the full diversity of the universe. So why do stars usually matter in planet formation? The short answer is gravity and material. When a star forms, it is born inside a massive cloud of gas and dust. As gravity pulls this cloud inward, most of the material falls into the center and becomes the star. But not all of it. A spinning disk of leftover gas and dust forms around the young star. This is called a protoplanetary disk. Inside this disk, tiny dust grains collide and stick together. Over time, they grow into pebbles. Pebbles grow into rocks. Rocks grow into planet-sized bodies. This process takes millions of years, and the star's gravity keeps the disk stable while it happens. In this classic picture, planets are a natural byproduct of star formation. Where there is a star, there are often planets. This is why for decades scientists assumed stars were required. Without a star, there would be no disk. Without a disk, there would be no planets. The logic was clean and simple. But simplicity can hide assumptions. Notice something important in everything we have said so far. The definition of a planet talks about mass, shape, and fusion, not about orbiting a star. Orbiting a star is common, but it is not what physically makes something a planet. Gravity does. A planet is a planet because of what it is, not because of what it circles. This idea opens the door to something strange. If a planet forms around a star and later gets thrown out, does it stop being a planet? Its shape does not change. Its mass does not disappear. It still does not produce fusion. The only thing that changes is its address. From a physical point of view, it is still a planet. This is why scientists began to rethink their assumptions. The universe is violent and chaotic, especially when star systems are young. Planets can collide, orbits can shift, giant planets can push smaller ones away. Entire worlds can be ejected into deep space. Once you accept that, the idea of a planet without a star stops sounding impossible. It starts sounding inevitable. There is another important detail. Some objects form directly from collapsing gas clouds without ever becoming stars. If the collapse stops early, the object never ignites fusion. Depending on its mass, it could end up looking very much like a planet, even though it never orbited a star at all. This challenges the old story that planets are always born as companions. When we ask whether planets can exist without stars, we are not just asking a scientific question. We are also confronting a habit of the human mind. That habit is bias, not a careless bias, but a natural one. We understand the universe by starting with what we can see, and for all of human history, what we could see was only one planetary system, our own. Everything we thought we knew about planets came from the sun and the worlds that move around it. Mercury, close and scorched, Venus hot and clouded, Earth alive and blue, Mars cold and red, Jupiter massive and powerful, Saturn elegant with rings, Uranus and Neptune distant and icy. This single arrangement shaped our imagination so deeply that it became the template for how we believed the entire universe must work. This is what we call solar system bias. It is the idea that what we observe locally must be true everywhere. From the moment early humans looked up at the sky, the sun dominated everything. It rose each morning, bringing warmth and light. It set each evening, plunging the world into darkness. It controlled seasons, harvests, survival itself. The sun was not just an object in the sky, it was life. So when ancient astronomers began to notice wandering points of light moving differently from the stars, they called them planets, meaning wanderers. But even then, those wanderers were still tied to the sun's path. They moved along the same sky road. They followed patterns connected to the sun's movement. The idea that a planet could exist without that central light never appeared, because nothing in the visible sky suggested it. Early models of the universe placed Earth at the center. Later models placed the sun at the center. But in both cases, planets were always defined by what they orbited. Orbit was everything. It was the organizing principle of the cosmos. As science advanced, this belief became stronger, not weaker. When Galileo turned his telescope toward the sky, he saw moons orbiting Jupiter. This was revolutionary, but it still reinforced the same pattern. Objects orbit something larger. Moons orbit planets. Planets orbit stars. Stars orbit something even larger. The universe seemed neatly layered and orderly. Even when Newton explained gravity, the bias remained. Gravity explained why planets orbit stars, not whether they had to. The equations described motion around massive bodies, and the most massive nearby body was always a star. Nothing in Newton's work suggested that planets could wander freely through space. The math allowed it, but imagination did not. Then came the age of classical astronomy, when scientists began to understand how stars form. They discovered nebulae, clouds of gas and dust collapsing under gravity. They saw that stars formed first and planets formed later from the leftover material. This was a powerful and elegant story. Stars were the creators, planets were the children. Once this story took hold, it shaped everything. Planet formation theories were built around stars. Telescopes were designed to look for planets around stars. Observations were interpreted through that lens. If you only look where you expect something to be, you rarely find surprises. Another major reason this assumption went unchallenged was the limit of human observation. For most of history, we could only see objects that produced or reflected significant light. Stars shine, planets reflect sunlight. A planet without a star would be almost completely dark. It would not glow. It would not reflect anything noticeable. To ancient and even early modern astronomers, such an object might as well not exist. Even with early telescopes, the situation did not improve much. Telescopes made stars brighter and sharper, but they did not suddenly reveal dark drifting planets. These objects are incredibly difficult to detect even today. Without light, they hide perfectly in the background of space. So science worked with what it could see. And what it could see reinforced the idea that stars come first and planets follow. There was also a psychological comfort in this model. A universe organized around stars felt stable and understandable. It mirrored human experience. We revolve around sources of energy. Life clusters around warmth and light. Order feels safer than chaos. A planet alone in the dark breaks that comfort. It suggests randomness, violence, instability. It suggests that worlds can be torn away from their origins and sent drifting forever. That idea did not fit well with the neat clockwork universe many scientists preferred for centuries. Another reason the assumption lasted so long was success. The star-centered model worked extremely well for explaining what we observed. It predicted planetary motions. It explained eclipses. It allowed accurate calendars. Later, it helped scientists discover new planets like Uranus and Neptune exactly where the math said they should be. When a model works, people stop questioning its boundaries. They focus on refining it, not challenging its foundations. Even when astronomers began finding planets around other stars in the 1990s, the bias deepened. These discoveries were celebrated as proof that our solar system was not unique. But notice the language. They were called exoplanets, planets outside our solar system, and every single one of them orbited a star. This seemed to confirm the old belief. Planets are everywhere, yes, but they always belong to stars. What scientists did not realize at first was that their methods were filtering reality. Most early planet hunting techniques relied on detecting a planet's effect on a star. A wobble, a dimming, a shift in light. No star meant no signal. No signal meant no discovery. So starless planets remained invisible, not because they were rare, but because our tools were blind to them. This is a crucial lesson in science. Absence of evidence is not evidence of absence. The universe does not stop existing where our instruments fail. There is also a deeper philosophical layer to this bias. Humans tend to define things by relationships. A moon is something that orbits a planet. A planet is something that orbits a star. A star is something that lights a system. These definitions feel intuitive, but they are not fundamental. They describe behavior, not essence. By defining planets through their relationship to stars, we locked ourselves into a narrow view. We confused a common arrangement with a requirement. It took new technology and a shift in thinking to break this pattern. When astronomers finally began detecting objects through gravitational effects, rather than light alone, cracks appeared in the old picture. Strange signals emerged. Objects with planetary mass but no visible star nearby. Worlds that did not fit the rules. At first, many scientists were cautious. Maybe these were errors. Maybe unseen stars were hiding. Maybe the data was wrong. That reaction itself was a sign of how deep the bias ran. The idea of a planet without a star felt more unbelievable than flaws in observation. But as evidence grew, the universe forced a correction. What became clear is that our solar system is not the standard blueprint. It is one outcome among many. Stars can form in crowded regions where gravity is chaotic. Planets can be pushed, pulled, stolen, or expelled. Systems can be torn apart before they ever settle down. In such an environment, starless planets are not exceptions. They are natural results. To understand why the idea of starless planets once felt impossible, we need to look closely at how planets are normally born. Not in theory, not in imagination, but in the slow, patient process that unfolds around young stars. This story is important because it explains why stars have always seemed essential. When you understand the traditional birth of planets, you also understand why the idea of planets without stars sounded like breaking a law of nature. Every planet's story usually begins with a star. Stars are born inside enormous clouds of gas and dust drifting through space. These clouds are cold, dark and vast, stretching across light years. Over time, gravity begins to pull parts of the cloud inward. As the material collapses, it starts to spin. The center becomes denser and hotter, eventually igniting nuclear fusion. A star is born. But the star does not form alone. Around the newborn star, a wide, flat disk of leftover material remains. This disk is made of gas, dust, ice particles, and microscopic grains. Scientists call this a protoplanetary disk. It looks calm from a distance, but inside it is a place of constant motion. collisions, and slow construction. This disk is where planets are made. At first, the material inside the disk is incredibly fine. Tiny dust grains smaller than grains of sand float through the gas. Gravity and static electricity cause them to stick together when they collide. 2 grains become 1, then 3, then thousands. Over time, these clumps grow larger and heavier. This stage is slow, painfully slow by human standards. It can take tens of thousands of years just for particles to grow from dust to pebble size. But gravity never stops working. As objects become more massive, their pull becomes stronger. They begin attracting more material. Pebbles become rocks. Rocks become boulders. Boulders become objects kilometers across. At this point, gravity starts to dominate the process. These growing bodies are called planetesimals, the building blocks of planets. Once planetesimals exist, the process speeds up. Larger objects collide with smaller ones and absorb them. Some collisions are gentle, others are violent. Some objects shatter, others merge. Over millions of years, a few dominant bodies begin to clear paths through the disk. These are the early planets. Closer to the star, where heat is intense, only rock and metal can survive. This is where rocky planets like Earth form. Farther out, where temperatures are lower, ice and gas are abundant. Here, giant planets like Jupiter and Saturn take shape, gathering thick atmospheres of hydrogen and helium. Throughout all of this, the star plays a central role. The star's gravity acts like an anchor. It holds the disk together. It keeps material from drifting away. It provides a stable center around which everything moves. Without that central mass, the disk would not remain organized long enough for planets to form. The star also provides energy. Heat from the young star shapes the disk's structure. Radiation pushes lighter elements outward. Stellar winds influence how gas flows. Even though planets do not make their own light, they are deeply affected by the light and heat of the star during their formation. Time is another crucial ingredient. Planet formation does not happen quickly. From the collapse of a gas cloud to the final shaping of planets, the process can take tens of millions of years. The disk itself does not last forever. Eventually, the star's radiation blows away remaining gas, ending the planet-building phase. This is important. The disk exists only because the star exists. The star forms first and the disk is a byproduct. Without the star, the disk disappears. Without the disk, planet formation stops. This is why, for so long, stars were seen as absolutely necessary. From this perspective, a planet without a star seems impossible. How could dust gather without an anchor? How could gravity organize material without a central mass? How could a disk survive long enough to build worlds? Everything in the standard model points back to the star. Even modern simulations reinforce this picture. When scientists model planet formation on computers, they place a star at the center. They add a disk. They let gravity and physics run. Planets appear naturally. Remove the star and the system falls apart. So the conclusion seemed obvious. No star, no disk. No disk, no planet. There is also the issue of stability. Planets are not just formed around stars, they are kept in place by stars. Orbiting a star provides a stable path through space. Gravity balances motion. This balance allows planets to exist for billions of years. Without a star, a planet has no orbit. It does not circle anything, it drifts. That drifting feels unstable, temporary, accidental. It feels like something that should not last. Early astronomers and physicists thought in terms of systems. A planet was part of a system, a star system, a solar system. The word planet itself was tied to motion around something greater. So when scientists imagined a planet without a star, it felt like imagining a leaf without a tree, or a shadow without an object. It did not fit the story. Another reason starless planets seemed impossible is energy. Stars provide heat. Heat drives geology. Heat melts ice. Heat powers atmospheres. Without a star, A planet would be frozen, inactive, and dead. That assumption made starless planets feel unimportant, even if they somehow existed. Why care about a frozen rock drifting in darkness? So science focused where life and activity seemed possible. Around stars. This focus shaped research priorities. Telescopes were designed to study stars. Detection methods looked for changes in starlight. Planet formation theories revolved around stellar environments. Anything outside that framework was ignored, not because it was disproven, but because it was unimagined. Yet hidden inside this standard story is an important clue. The process relies on gravity, dust, gas, and time. The star organizes these elements, but gravity itself does not belong to stars alone. Gravity exists wherever mass exists. Dust exists everywhere. Gas fills the galaxy. Time is abundant. The star is a powerful organizer, but it is not the only possible one. At first glance, the birth of planets around stars makes starless planets seem impossible. But that feeling comes from familiarity, not necessity. We are used to this method because it is common and efficient, not because it is the only one nature allows. This is the tension at the heart of modern astronomy. The classic model explains a lot, but not everything. It explains how planets like Earth form. It explains why most planets we detect orbit stars. But it does not explain what happens when systems break apart. It does not explain chaos. It does not explain failure. Young star systems are not calm places. They are violent. Stars form in clusters. Gravity pulls in many directions at once. Massive planets can disrupt smaller ones. Close stellar encounters can tear disks apart. Supernovae can blast systems with energy. In such an environment, not every planet stays where it was born. Some are thrown out. For a very long time, planets without stars existed only as a strange idea at the edge of theory. They were discussed quietly, if at all. Most astronomers assumed that if such worlds existed, they would be extremely rare, perhaps the result of some unusual accident. There was no strong motivation to look for them, and no clear way to find them. Then slowly, and almost by mistake, the universe revealed something that forced science to rethink everything. The first evidence of planets without stars did not come from a planned search. It came from confusion. In the late 20th century, astronomers began using new techniques to study distant regions of the Milky Way. They were no longer just mapping stars. They were trying to understand how mass is distributed in the galaxy, how much matter is visible, how much is hidden, how does gravity behave on large scales. One of the most powerful tools for this work was a strange effect predicted by Einstein's theory of general relativity, called gravitational lensing. According to Einstein, massive objects bend space itself. When light from a distant star passes near a massive object, that light bends, causing the star to briefly appear brighter or distorted. This effect works even if the massive object itself gives off no light. At first, astronomers used gravitational lensing to study galaxies and dark matter, but then they noticed something odd. In dense star fields, especially toward the center of the Milky Way, some stars would suddenly brighten for a short time and then fade back to normal. This was expected, but in a few cases the brightening was extremely brief, too brief to be caused by a star or even a brown dwarf. Something small had passed in front of the background star, something with mass but no light. At first, these events were dismissed as noise or errors. The data was messy. Observations were difficult. The galaxy's center is crowded, dusty, and chaotic. Many astronomers assumed the signals were coming from faint stars that had not yet been catalogued, but the signals kept appearing. As surveys improved, the number of these short lensing events grew, and the math began to tell a strange story. The mass causing the lensing was similar to that of planets. Not stars, not failed stars, planets, and there was no visible star nearby. This was the first real crack in the old worldview. Astronomers realized that they were seeing objects with the mass of planets, floating freely through space, completely unattached to any star. These objects were not orbiting anything detectable. They were simply passing through the galaxy like cosmic ghosts. The discovery was accidental because no one was looking for planets this way. Planet hunting at the time relied almost entirely on stars. Astronomers measured how stars wobble or dim when planets orbit them. Without a star, those methods fail completely. A starless planet leaves no wobble, no shadow, no regular signal. Gravitational microlensing changed that. It allowed astronomers to detect mass itself, regardless of light. But accepting this idea was not easy. The early reaction was skepticism. Healthy skepticism, but skepticism nonetheless. Scientists asked reasonable questions. Could these signals be coming from distant, faint stars? Could they be brown dwarfs that were too dim to detect? Could they be statistical flukes? Some argued that the objects were not planets at all, but failed stars. Others suggested that the background stars were behaving strangely. A few even questioned whether microlensing could be trusted at such small scales. This debate lasted for years. The problem was not the data alone, it was the implication. If these objects were truly planets, without stars, then the number of planets in the galaxy could be far higher than anyone imagined. It would mean that planetary systems are not stable by default. It would mean chaos is common. For astronomers who had spent decades building models around neat star-centered systems, this was deeply unsettling. Another shock came from numbers. As more microlensing surveys were conducted, scientists began estimating how many of these free-floating planets might exist. The results were staggering. Some studies suggested that there could be as many rogue planets as stars in the Milky Way. Others suggested even more. Think about that for a moment. If true, it would mean that the most common type of planet in the galaxy might not orbit a star at all. The universe would be filled with dark worlds, drifting silently between suns. This idea felt almost offensive to the old intuition. Planets were supposed to be companions, not wanderers. They were supposed to belong somewhere. The shock was not just scientific, it was emotional. Astronomy has always carried a sense of order, orbits, cycles, predictability. Even when discoveries were strange, they often fit into a larger pattern. Rogue planets did not fit. They suggested loss, violence, and instability. They suggested that planetary systems fail often, that worlds are regularly thrown away. As evidence grew, resistance softened. Independent teams confirmed similar results. Different surveys, using different methods, found similar populations of starless objects with planetary mass. Some were found in young star clusters, where gravitational chaos is intense. Others were found in quieter regions, far from obvious stellar nurseries. This raised new questions. Were all these planets ejected from star systems? Or could some form on their own? The debate shifted. It was no longer about whether starless planets existed. It was about how they came to be. The discovery also forced astronomers to confront their own assumptions. They realized that for decades, their instruments had been biased. They were excellent at finding planets where they expected them to be. Around stars, close in, bright enough to influence starlight. They were terrible at finding planets everywhere else. This realization echoed through the scientific community. How many other things were being missed simply because no one was looking the right way? The discovery of planets without stars also changed how scientists thought about planetary survival. A planet does not need a star to remain physically intact. It does not fall apart. It does not evaporate instantly. It continues drifting, holding itself together by gravity. This challenged the idea that stars are guardians. They are creators, yes, but they are also sources of disruption. Massive planets can destabilize systems. Stellar encounters can rip planets away. Supernovae can blast systems apart. In this light, rogue planets stopped looking like failures. They started looking like survivors. The shock spread beyond astronomy into philosophy and science communication. Popular science articles began calling these worlds orphan planets and lonely worlds. Artists imagined frozen landscapes under eternal night. Writers speculated about hidden oceans and underground life. The public reaction mirrored the scientific one. Fascination mixed with disbelief. How could something so large and important exist in complete darkness? But perhaps the deepest shock came from what this discovery implied about life. If planets without stars are common, then life may not be limited to warm, sunlit surfaces. It may exist in places we never thought to search, deep underground, powered by chemistry instead of light, protected beneath ice. Suddenly the question of habitability expanded. The universe felt bigger, not just in size but in possibility. The discovery that changed everything was not a single moment. It was a slow realization, a collection of strange signals, a series of debates, a gradual acceptance that the universe is far less orderly than we imagined. Planets without stars were not just a new category. They were a reminder that nature does not follow our expectations, a reminder that what we see is shaped by how we look, and a reminder that even in the darkest places, the universe is still building worlds. With that realization, astronomy crossed a line it could never step back from. The universe was no longer just a collection of star systems. It was a sea of wandering planets, silent and unseen, waiting to be understood. When astronomers finally accepted that planets can exist without stars, a new category of worlds came into focus. These planets did not orbit suns. They did not belong to neat planetary systems. They wandered through space on their own. Scientists gave them a simple but powerful name: rogue planets. Rogue planets are also called free-floating planets or orphan planets. All three names describe the same idea. These are planetary mass objects that drift through the galaxy without being gravitationally bound to any star. They are not moons, they are not failed stars. They are real planets, but they are alone. At first, the name rogue sounded dramatic, almost rebellious, but it fits. These worlds have broken free from the structures that usually define planets. They exist outside the traditional order of star and orbit. And once you understand what they are and how they move, you begin to see that they may not be rare exceptions at all. They may be one of the most common types of planets in the universe. A rogue planet is defined by what it does not do. It does not orbit a star. That is the key difference. In every other way, it can be just like a familiar planet. It can be rocky like Earth. It can be gaseous like Jupiter. It can have an atmosphere. It can have moons. It can even generate internal heat. The only thing missing is a sun. This absence changes everything about the planet's environment. Without a star, there is no sunlight to warm the surface, no day and night cycle, no seasons. The sky would be black, filled only with distant stars and galaxies. The surface temperature would drop extremely low, often hundreds of degrees below freezing. Any atmosphere the planet once had may partially freeze or collapse. Yet the planet itself remains intact. Gravity still holds it together. Its core still exists. In some cases, geological processes may continue deep below the surface. But how does such a planet move through space? Unlike planets in star systems, which follow predictable orbits, rogue planets travel on long, lonely paths through the galaxy. Their motion is determined by the same forces that move stars. They orbit the center of the Milky Way, following vast arcs that can take hundreds of millions of years to complete. In this sense, rogue planets are more like stars than traditional planets. They move independently, responding to the overall gravitational field of the galaxy rather than a nearby sun. Their paths can be tilted at any angle. They can pass through star-forming regions, glide between spiral arms, or drift through the quiet outskirts of the galaxy. Some move slowly, others travel at tremendous speeds, especially if they were violently ejected from their original systems. A close encounter with a massive planet or a neighbouring star can fling a planet outward like a stone from a sling. Once it escapes the gravity of its star, it is free forever. This brings us to an important question. Why are rogue planets not tied to any star? The most common reason is chaos during the early days of star system formation. Stars rarely form alone. They are born in clusters, surrounded by other young stars. These environments are crowded and unstable. Gravitational forces pull in many directions at once. Massive planets can migrate inward or outward. Orbits can cross. Collisions can occur. In such a chaotic setting, some planets are doomed. If a young planet passes too close to a giant planet, it can be gravitationally kicked outward. If it gains enough speed, it can escape the entire system. This process is surprisingly efficient. Simulations show that planetary systems can lose a significant fraction of their planets during their early evolution. Another cause is stellar encounters. When stars pass close to each other in dense clusters, their gravity can disrupt each other's planetary systems. Planets can be stolen, swapped, or thrown into space. The star that loses a planet may never notice. The planet, however, becomes a rogue. Supernova explosions can also play a role. When a massive star explodes, it can suddenly lose a large amount of mass. This weakens its gravitational grip on surrounding planets. Some may drift away, others may be flung outward by the blast. Not all rogue planets are created by violence, though. There is growing evidence that some rogue planets may form alone, without ever orbiting a star. In certain regions of space, dense clumps of gas can collapse directly into planetary mass objects without becoming stars. These objects blur the line between planets and brown dwarfs, but many fall squarely within the planetary mass range. If this process is common, it means that the galaxy is capable of producing planets in more than one way. Stars are not always required as parents. So how common are rogue planets? This is where the story becomes truly surprising. Based on microlensing surveys and computer models, astronomers estimate that there may be billions of rogue planets in the Milky Way. Some studies suggest that for every star in the galaxy, there could be one or even several free-floating planets. That means rogue planets could rival stars in number. If true, this completely changes how we think about the population of planets in the universe. Most planets may not orbit stars at all. The night sky, which looks empty between stars, may actually be filled with invisible worlds. We do not see them because they do not shine. This invisibility makes them difficult to study. Most rogue planets are detected only briefly when they pass in front of a distant star and bend its light. These events are rare and unpredictable. Each detection is a momentary glimpse, a shadow passing across a cosmic stage. Yet even with limited data, patterns are emerging. Rogue planets appear in a wide range of masses. Some are small and rocky, others are as massive as Jupiter. Some may even have moon systems that survived their ejection. Their ages also vary. Some are young, still warm from formation. Others are ancient, having drifted through space for billions of years. This diversity suggests that rogue planets are not a single class of objects. They are a population shaped by many different histories. One of the most fascinating aspects of rogue planets is how they challenge our ideas of importance. For a long time, planets were considered interesting mainly because of their relationship to stars. They were secondary, dependent. Without a star, a planet seemed irrelevant. Rogue planets force us to abandon that thinking. These worlds have their own stories. They have their own internal processes. Some may have thick atmospheres that trap heat. Some may have subsurface oceans kept warm by radioactive decay. Some may be completely frozen and inactive. But they are still planets. And because they are so numerous, they may play an important role in the galaxy's evolution. They carry mass. They influence gravity on small scales. They may even act as seeds for new systems if they are captured by stars later in their journeys. In rare cases, a rogue planet may pass close enough to a star to be captured, becoming a planet once again. This means some planetary systems may include worlds that were born elsewhere, wandered the galaxy, and eventually found a new home. In this way, rogue planets are not just lonely wanderers. They are travelers, messengers of chaos and movement, evidence that the galaxy is not a static collection of systems, but a dynamic environment where worlds are constantly being rearranged. So when we talk about worlds without suns, we are not talking about mistakes or leftovers. We are talking about a major class of cosmic objects, a hidden population that challenges our sense of order. Rogue planets remind us that the universe does not care about neat definitions. It builds, it breaks, and it moves on. And in that process, it fills the darkness with worlds we are only just beginning to understand. To understand how planets lose their stars, we need to let go of the peaceful image we often have of planetary systems. From far away, star systems look calm and orderly. Planets glide along smooth paths. Everything seems balanced and permanent. But this calm picture is misleading. In reality, the birth and early life of a star system is one of the most violent and chaotic processes in the universe. Planets do not begin their lives in quiet harmony. They are born in turbulence. Stars are born inside dense regions of gas and dust called stellar nurseries. These regions are crowded. Hundreds or even thousands of stars can form close together, all within a relatively small volume of space. Each young star pulls on the surrounding material with its gravity. These gravitational forces overlap, interfere, and compete. From the very beginning, nothing is isolated. As a star forms, its planets begin forming at the same time. But these planets do not appear one by one in clean orbits. Many planetary embryos form together. They grow, migrate, and interact. Their paths cross. Their gravity tugs on each other. Some collide and merge, others scatter each other outward. This is where instability begins. In young systems, giant planets often form early. These massive worlds dominate the gravitational environment. Even a single Jupiter-sized planet can disrupt the orbits of many smaller planets. If there are two or more giant planets, the system can become extremely unstable. Imagine several massive objects circling a young star, each pulling on the others. Over time, small changes grow larger. Orbits stretch and tilt. Close encounters become more frequent. Eventually, one planet passes too close to another. In that moment, gravity does something dramatic. It transfers energy. One planet may be thrown inward, crashing into the star or another planet. The other may be thrown outward, gaining speed. If that speed is high enough, the planet escapes the star's gravitational grip completely. This is planetary ejection. Once a planet is ejected, there is no return. The star can no longer pull it back. The planet becomes a rogue, drifting through space alone. Computer simulations show that this process is not rare. In fact, it may be common. Many models suggest that young planetary systems routinely eject planets, especially smaller ones. Some systems may lose half or more of their original planets during their early evolution. The violence does not end there. Stars do not form in isolation. They form in clusters. As these clusters evolve, stars pass close to each other. When two stars come near, their gravity can tear at each other's planetary systems. Orbits can be distorted. Planets can be captured by the other star or flung outward into space. These stellar encounters are especially common in the first few million years of a star's life, when clusters are dense. A single close pass can be enough to destabilize an entire planetary system. Even if a planet avoids early ejection, it is not guaranteed safety. Stars themselves change over time. They age, they evolve, and some die violently. When a massive star reaches the end of its life, it explodes in a supernova. This explosion releases an enormous amount of energy and ejects a large portion of the star's mass into space. Gravity depends on mass. When mass is suddenly lost, gravity weakens instantly. Planets that once orbited securely may suddenly find themselves moving too fast for the star's reduced gravity. Their orbits stretch outward, some become unstable, some escape entirely. In this way, a supernova can turn a normal planetary system into a source of rogue planets. Even stars like the Sun, which will not explode, can cause planetary loss. As they age, they expand into red giants. They lose mass through stellar winds. Over time, this mass loss can slowly weaken their grip on distant planets. Some may drift away, especially if their orbits were already disturbed. There is also the role of binary and multiple star systems. Many stars are not alone. They exist in pairs or groups. In these systems, gravity is far more complex. Planets may orbit one star, or both, or move between unstable paths. Changes in the star's orbits can destabilize planets over time, leading to ejection. In some cases, planets are born into unstable situations from the start. Then there is the influence of the galaxy itself. As stars orbit the center of the Milky Way, they pass through regions with varying gravitational forces. Encounters with molecular clouds, passing stars, or even the tidal forces of the galaxy can perturb planetary systems over billions of years. These effects are subtle, but given enough time, they add up. A planet does not need to be violently thrown out in a single moment. It can slowly drift outward as its orbit becomes more and more stretched. Eventually, one final nudge is enough to send it free. So how exactly does a planet get kicked into deep space? The key concept is escape velocity. Every star has a gravitational pull strong enough to keep planets bound. But if a planet gains enough speed, it can overcome that pull. This speed can come from close encounters with other planets, from interactions with passing stars, or from changes in the star itself. Once a planet exceeds escape velocity, it no longer follows a closed orbit. It follows an open path. It leaves the system forever. From that moment on, the planet's story changes completely. It no longer has a sun. It no longer has seasons. It no longer has a stable source of energy. It begins a journey that may last billions of years, drifting through the galaxy, unseen and silent. What is striking is how natural this process is. Nothing about planetary ejection requires rare conditions. It does not require unusual physics. It is simply gravity doing what gravity always does. When many massive objects interact, some are bound and some are thrown away. This is not failure, it is redistribution. The same forces that build planets also scatter them. The same gravity that holds systems together can tear them apart. The universe does not aim for stability, it explores all possibilities. This realization changes how we see rogue planets. They are not mistakes, they are not accidents. They are expected outcomes of a dynamic universe. In fact, if planetary systems never lost planets, that would be strange. Given how crowded and violent star-forming regions are, it would be surprising if every planet stayed neatly in place. Chaos is not the exception, it is the rule. So when we ask how planets lose their stars, the answer is not one single event. It is a collection of processes acting over time. Early chaos, gravitational battles, stellar encounters, star death, galactic tides, each one can loosen a planet's bond. Together, they ensure that some worlds will always be set adrift. For a long time, scientists believed there was only one way to make a planet. First, a star forms. Then planets grow quietly in a disk around it. This idea felt complete, logical, almost unquestionable. But once rogue planets were discovered in large numbers, a new and uncomfortable question appeared. What if some planets were never thrown out? What if some planets were never attached to a star at all? This question pushes science into uncertain territory. It forces astronomers to rethink how planets begin, not just how they end up alone. And the answer is not simple. In fact, this is one of the most active and debated areas in modern astronomy. Let us start with what we know. The classic story of planet formation depends on stars. A collapsing gas cloud forms a star. Leftover material forms a disk. Planets grow inside that disk. This model explains our solar system and many others we have observed. But it may not explain everything. The universe is not a controlled laboratory. It is messy, uneven, and full of extremes. Gas clouds come in many sizes and densities. Gravity does not always behave in neat, predictable ways. And nature rarely follows only one rule. This is where new theories begin. Some astronomers now believe that under the right conditions, gas clouds may be able to form planet-sized objects directly, without ever forming a star. These objects would not be ejected planets. They would be born alone. Imagine a cold, dense region inside a giant molecular cloud. Gravity begins to pull material inward, just like in star formation, but this time, the collapsing clump does not have enough mass to ignite nuclear fusion. It never becomes a star. It never shines. Instead, it collapses just far enough to form a compact planet-sized object. If this happens, the result looks like a planet. It has mass. Gravity shapes it into a sphere. It does not produce fusion, but it never orbited a star. It never had a parent sun. This idea sounds radical, but it is not forbidden by physics. Gravity does not care what we call an object. It only cares about mass and density. If a gas cloud fragment reaches planetary mass and stabilizes before becoming a star, it will simply exist as a dark object. The problem is not whether this is possible. The problem is how often it happens. This leads us to a very confusing boundary in astronomy. The line between planets and failed stars. Between planets and stars lies a category called brown dwarfs. These objects are larger than planets but smaller than stars. They are often described as failed stars because they never sustain full hydrogen fusion. Some burn a limited type of fuel early in their lives. Others barely burn anything at all. Brown dwarfs form like stars. They collapse directly from gas clouds. They do not need disks. They do not need stars. So here is the critical question. If brown dwarfs can form directly from gas clouds, why not planets? The difference comes down to mass. Stars are massive. Brown dwarfs are less massive. Planets are even less massive. But there is no sharp cutoff where nature suddenly changes its behavior. The boundaries are fuzzy. Some brown dwarfs have masses only a few times greater than Jupiter. Some planets are nearly as massive as small brown dwarfs. From the outside, they can look almost identical. So how do we tell them apart? Traditionally, scientists used formation history. If an object formed in a disk around a star, it was called a planet. If it formed directly from cloud collapse, it was called a brown dwarf. But here is the problem. For rogue planets, we often do not know their history. We see them drifting through space. We can estimate their mass, but we do not know how they were born. That means some objects we call rogue planets might actually be low-mass brown dwarfs. And some objects we call brown dwarfs might actually be planets that formed alone. The universe does not label its creations. Humans do. This uncertainty is one of the biggest challenges in the field. Some astronomers argue that true planets must form in disks. According to this view, planets cannot form directly from gas clouds because the physics favors fragmentation into larger objects. Below a certain mass, collapse should stop. Others disagree. They point to simulations showing that turbulent gas clouds can fragment into a wide range of masses, including planetary ones. In chaotic environments, small clumps can form and survive. There is also observational evidence hinting that something like this may be happening. In young star-forming regions, astronomers have detected free-floating objects with masses similar to planets, moving alongside young stars. These objects appear too young to have been ejected. They may have formed at the same time as stars, but independently. If true, this would mean that planets can form in parallel with stars, not just as their companions. Another idea suggests a hybrid path. Some planets may begin forming in disks, but get ejected very early, before the system stabilizes. These planets would technically form with stars, but would spend almost their entire existence alone. From an observational point of view, they would be indistinguishable from planets that formed independently. This blurs the distinction even further. So where does science stand right now? The honest answer is uncertainty. We know rogue planets exist, we know many are ejected, we suspect some may form alone. But we do not yet know the balance between these pathways. We also do not know how low in mass direct collapse can go. Can Earth mass objects form this way, or only Jupiter mass ones? Can rocky planets form without disks, or only gas giants? These questions remain open. Another major unknown is frequency. If independent planet formation is rare, then most rogue planets are ejected worlds. If it is common, then the galaxy may be producing planets constantly, even in regions without stars. The implications are enormous. If planets can form without stars, then planets may exist in places we never thought to look. Between star systems, in dark molecular clouds, in the quiet outskirts of galaxies. The population of planets would explode beyond current estimates. It would also change how we think about habitability. A planet born without a star would never experience warmth or light, but it might still have internal heat. It might still have chemistry. It might still have underground environments where life could exist. This pushes the idea of life beyond traditional boundaries. Life would no longer be tied to stars. It would be tied to energy, chemistry, and time. At the same time, caution is necessary. Science advances slowly for good reasons. Extraordinary claims require strong evidence. While models and observations suggest the possibility of starless planet formation, direct proof is difficult. We cannot rewind the universe to watch these objects form. We must infer their histories from faint signals, limited data, and careful statistics. Future telescopes may help. More sensitive microlensing surveys, infrared observatories that can detect faint heat signatures, better simulations that test extreme conditions. Until then, this question remains one of the most exciting uncertainties in astronomy. Can planets form without stars? The answer is no longer a simple no. It is a cautious maybe. What is clear is that the universe is far more flexible than we once believed. It does not follow a single recipe. It experiments. It tries. It's different paths. And sometimes it creates worlds in complete darkness without ever lighting a sun. And that possibility alone is enough to change how we see planets forever. To imagine life on a starless planet, we first have to let go of everything we associate with a normal world. No blue sky, no sunlight, no warmth spreading across a surface at dawn. No shadows moving with time. A planet without a star is not just Earth with the lights turned off. It is a fundamentally different kind of place. The most striking feature of a starless planet is darkness. Not night, not twilight, permanent darkness. On Earth, darkness is temporary. Even on the darkest night, the sun still exists somewhere. The planet is only turned away from it. On a rogue planet, there is no sun at all. No nearby star to rise, no horizon that ever brightens. The sky would be black at all times, filled with distant points of light from faraway stars and galaxies, but none close enough to matter. If you stood on the surface, there would be no natural light source, no blue glow, no warm colours, only faint starlight, so weak it would barely illuminate anything at all. The landscape would exist in shadow, revealed only if the planet itself produced light in some way, such as glowing lava, lightning, or auroras. Darkness would not just be a visual experience, it would shape everything. Without sunlight, the surface temperature of a starless planet would drop rapidly. Heat escapes into space and nothing replaces it. Over millions of years, the planet would become extremely cold. Colder than Antarctica. Colder than the coldest nights on Mars. In many cases, surface temperatures could fall below -200 degrees Celsius. Water, if it exists on the surface, would freeze solid. Oceans would become thick shells of ice, Atmospheres could partially freeze and fall as snow made of gases like carbon dioxide or nitrogen. The surface would become hard, brittle, and silent. There would be no weather in the way we understand it, no rain driven by sunlight, no wind powered by temperature differences between day and night. The planet's surface would feel dead and motionless, and there would be no sunrise. This is difficult to fully grasp because sunrise is more than light, it is time. It is rhythm. On Earth, life is organized around the rising and setting of the sun. Plants grow towards it, animals wake and sleep by it. Seasons change as the planet tilts and moves. On a starless planet, there is no day, no night, no year. Time still passes, but there are no natural markers. If the planet rotates, it rotates in darkness. If it tilts, the tilt means nothing without a star to create seasons. The concept of morning and evening disappears completely. This absence of cycles would reshape any environment that exists. The surface of such a planet would likely look alien and empty. Imagine a frozen desert stretching endlessly in every direction. The ground might be covered in ice, dust, or frozen gases. Mountains would stand black against a black sky. Craters would never be softened by erosion from rain or wind. Without sunlight, colours would be muted or invisible. Ice would not sparkle, rocks would not shine. Everything would appear grey or black unless artificial light was introduced. But despite this harsh picture, the surface might not be completely inactive. Some rogue planets may still have internal heat. Planets are not just cold rocks floating in space. Many contain heat trapped from their formation. Radioactive elements inside their cores slowly release energy. In some cases, this heat can last for billions of years. If a rogue planet is large enough, like Jupiter or larger, it may retain significant internal warmth. This heat could slowly rise toward the surface, creating cracks in the ice, volcanic activity, or even subsurface oceans. In rare places, the surface might glow faintly from geothermal activity. Lava flows could light small regions with dim red light. Ice might melt locally, creating strange frozen landscapes shaped by heat from below rather than light from above. The surface would not be shaped by sunlight, but by gravity and internal energy. Without erosion from liquid water or wind, the planet would preserve its features for a very long time. Craters from ancient impacts would remain sharp. Geological scars would last for billions of years. This makes starless planets like time capsules, preserving their history in frozen form. But what about life? On the surface, life as we know it would struggle. Without sunlight, photosynthesis is impossible. Plants cannot grow. Food chains based on light cannot exist. The surface would be one of the most hostile environments imaginable. If life existed, it would almost certainly not live on the surface. Instead, scientists look downward. Beneath thick layers of ice, conditions may be very different. Internal heat could keep water liquid below the surface. Pressure from the ice above could prevent it from freezing. In these hidden oceans, life would be shielded from the cold and darkness above. On Earth, we already see examples of life that survives without sunlight. Deep in the ocean, near hydrothermal vents, organisms live off chemical energy instead of light. Bacteria use heat and minerals to survive. Entire ecosystems exist in complete darkness. A starless planet could offer similar conditions, but on a much larger scale. If such a planet has a thick, icy shell and a warm interior, it could host a global subsurface ocean. Life there would never know what a star is. It would never experience a sunrise. Its entire existence would unfold in darkness, guided only by chemistry and heat. From the surface, the planet would look dead. From the inside, it might be quietly alive. Even if life does not exist, the environment itself challenges our imagination. A world without a star is not dramatic in the way exploding stars or black holes are. It is quiet, still, lonely. Its story is written in silence rather than light. Yet these planets may be incredibly common. That means the galaxy could be filled with frozen worlds, drifting through space, each one carrying a unique surface shaped by darkness and cold. Some may be ancient beyond comprehension, some may still be warm from their violent birth. When we imagine life on a starless planet, we must resist the urge to judge it by Earth's standards. These worlds are not failed Earths, they are not broken planets. They are simply built for a different kind of existence. They show us that a planet does not need sunlight to be a planet, and life, if it exists, may not need sunlight to survive. The surface of a starless planet may be one of the most extreme environments in the universe, but beneath that frozen silence, the universe may still be quietly at work, doing what it has always done, building worlds, testing possibilities, and reminding us that light is not the only way for a planet to exist. When we imagine a planet without a star, the first image that comes to mind is a frozen, dead world. A dark ball of ice drifting through space, colder than anything we can imagine. That image feels logical. Without a sun, there should be no heat. Without heat, everything should freeze solid. But the universe is rarely that simple. One of the most surprising discoveries in planetary science is this. Not all heat comes from stars. In fact, many planets carry their own energy deep inside them. This hidden heat can last for billions of years, long after a planet has lost its sun. And because of this internal energy, many starless planets may not be completely frozen after all. To understand this, we need to travel beneath the surface of a rogue planet and explore what is happening inside. Every planet begins hot. When a planet forms, whether around a star or by another process, it starts its life full of energy. As material falls together under gravity, it releases heat. Collisions between rocks, dust, and gas generate enormous amounts of energy. Large impacts can melt entire regions. The early planet becomes a glowing, molten object. This heat does not disappear overnight. Even after the surface cools, much of that energy remains trapped deep inside the planet. Rock and metal are poor conductors of heat. They hold onto warmth for extremely long periods. On Earth, the core is still incredibly hot, even after 4.5 billion years. A rogue planet begins its lonely journey, already carrying a thermal memory of its birth. This brings us to the first major source of hidden heat, planetary cores. Inside most planets is a core made of dense materials like iron and nickel, surrounded by layers of rock or ice. In massive planets, pressure is intense. Atoms are squeezed tightly together. This pressure alone creates heat, but pressure is only part of the story. Inside planetary cores, there are radioactive elements such as uranium, thorium, and potassium. These elements are unstable. Over time, they slowly break down in a process called radioactive decay. When they decay, they release energy in the form of heat. This process is slow, steady, and incredibly long-lasting. On Earth, radioactive decay is one of the main reasons the interior remains hot. It drives volcanic activity, plate tectonics, and the movement of molten rock beneath the crust. Without it, Earth would have cooled and become geologically dead long ago. Now imagine a rogue planet with a similar composition. Even without a star, radioactive decay would continue. Heat would still be produced. Deep below the surface, temperatures could remain high enough to keep rock partially molten or water in liquid form. This alone challenges the idea that starless planets must be completely frozen. The second source of hidden heat comes from residual heat from formation. Planet formation is violent, massive impacts, rapid accretion, compression. All of these processes generate heat. In large planets, especially gas giants and ice giants, this heat can be enormous. Jupiter, for example, radiates more heat than it receives from the Sun. Much of this energy comes from residual heat left over from its formation, slowly leaking out over time. If Jupiter were ejected from the solar system and became a rogue planet, it would not instantly freeze. It would continue glowing faintly in infrared light for billions of years. This means that large rogue planets could remain surprisingly warm internally, even in the coldest regions of space. Smaller rocky planets cool faster, but even they can retain heat for very long timescales, especially if they are massive, dense, and rich in radioactive elements. This brings us to a third and more surprising heat source, tidal heating. Tidal heating usually happens when a planet is pulled and stretched by the gravity of another object, such as a star or a moon. This stretching creates friction inside the planet, generating heat. At first, it seems impossible for a rogue planet to experience tidal heating. After all, it has no star. But some rogue planets may not be completely alone. Many planets have moons. If a planet is ejected from its star system, some of its moons may remain bound to it. In fact, simulations suggest that moon systems can survive planetary ejection surprisingly well. If a rogue planet has one or more large moons, gravitational interactions between the planet and its moons can create tidal forces. These forces flex the planet's interior, generating heat. A powerful example of this in our solar system is Jupiter's moon, Io. Io is incredibly volcanic, not because of sunlight, but because of tidal heating caused by Jupiter's gravity. Now imagine a rogue planet with a massive moon locked in a tight orbit. Even in total darkness, tidal heating could keep parts of the planet warm. It could maintain molten regions inside. It could drive geological activity. In rare cases, the moon itself could be heated enough to have subsurface oceans. This means that some rogue planets may host entire systems of internal energy exchange long after leaving their stars behind. Another factor that affects heat retention is size. Large planets lose heat more slowly than small ones. This is because volume increases faster than surface area as size increases. A massive planet has a lot of material to store heat and relatively less surface area through which to lose it. This is why gas giants and ice giants are especially interesting candidates for hidden heat. Their thick atmospheres also act like insulation, trapping warmth inside. Some rogue planets may have atmospheres thick enough to retain heat efficiently, even without sunlight. These atmospheres could slow cooling dramatically. In such cases, surface temperatures might be higher than expected. Still extremely cold by Earth standards, but not as lifeless as once imagined. This leads to a critical realization. A starless planet is not defined only by its surface temperature. What matters is what happens beneath the surface. If internal heat is strong enough, it can keep water liquid under thick layers of ice. It can drive chemical reactions. It can create environments that are stable for billions of years. In other words, a rogue planet can be geologically alive even if it is astronomically dark. This is why scientists now say that not all starless planets are completely frozen. Some are frozen solid, especially small ones that lost heat quickly. Others are cold on the outside but warm inside. A few may even have active geology, volcanic vents or subsurface oceans. The difference depends on mass, composition, age and history. A young rogue planet, recently ejected, may still be glowing with internal heat. An ancient one may be nearly frozen. A massive gas giant may remain warm far longer than a small rocky world. This diversity makes rogue planets incredibly interesting scientific targets. They are not uniform. They are not all dead. They represent a wide range of thermal states, from frozen relics to quietly active worlds. From the outside, they may all look the same, dark, cold, invisible, but inside they tell very different stories. This hidden heat changes how we think about habitability. Life does not require sunlight, it requires energy. On Earth, sunlight is the dominant energy source, but deep below the ocean, life thrives on chemical energy from Earth's interior. A rogue planet with internal heat could provide similar conditions, protected from space by thick ice, powered by radioactive decay and tidal forces, stable over immense timescales. Such life would never see a star. It would never know warmth from above, but it could exist nonetheless. This idea does not mean that life is common on rogue planets. That remains unknown, but it does mean that starless planets are not automatically lifeless. They are not just frozen rocks drifting through space. They are worlds with interiors, with energy, with history. Hidden heat transforms rogue planets from simple cosmic leftovers into complex dynamic objects. It reminds us that the absence of light does not mean the absence of activity. In the deep darkness of space, warmth can still exist, movement can still happen, and planets can still be alive in ways we are only beginning to understand. When scientists talk about the possibility of life on starless planets, they are not imagining forests, animals, or oceans open to the sky. They are looking much deeper, beneath kilometers of ice, beneath frozen surfaces that never see light. This is where one of the most fascinating ideas in modern science begins: underground oceans on rogue planets. At first, the idea sounds unbelievable. How could liquid water exist on a planet with no sun? How could an ocean survive in eternal darkness and extreme cold? The answer lies in heat that does not come from stars. As we have seen, many planets carry internal energy. This heat rises slowly from the core toward the surface. On a starless planet, the surface may be frozen solid, but the heat below can be strong enough to keep water liquid under thick layers of ice. This creates an ice-covered ocean, sealed away from space, protected from radiation, and stable for very long periods of time. To understand why scientists take this idea seriously, we do not need to look far. We can look right here in our own solar system. Europa, one of Jupiter's moons, is a frozen world. Its surface is a shell of ice, cracked and fractured. Sunlight at Europa's distance is weak. The surface is extremely cold, and yet, beneath that ice there is strong evidence of a global ocean of liquid water. Europa's ocean exists not because of sunlight, but because of internal heating. Jupiter's gravity stretches and squeezes Europa as it orbits, generating heat through tidal forces. This heat prevents the ocean from freezing. Enceladus, a small moon of Saturn, tells a similar story. Enceladus is tiny compared to planets. Its surface temperature is far below freezing, and yet it has active geysers that spray water vapor and ice into space. These plumes come from a subsurface ocean kept warm by tidal heating. What makes these moons so important is this: they show us that liquid water does not require a star. If small moons can maintain oceans without direct sunlight, then large planets, especially massive rogue planets, may be even better candidates. A rogue planet with sufficient internal heat and a thick, icy shell could host a vast underground ocean, possibly larger than all of Earth's oceans combined. These oceans would be dark, silent, isolated, but they would be liquid, stable, and chemically active. This brings us to the next big question: could life survive in such an environment? To answer that, we need to rethink what life actually needs. On Earth, most life depends on sunlight, directly or indirectly. Plants use photosynthesis. Animals eat plants or other animals. The entire surface ecosystem is powered by the sun. But Earth has another biosphere, one that exists completely without sunlight. Deep in the oceans, far below the reach of light, life thrives around hydrothermal vents. These vents release hot, mineral-rich water from the Earth's interior. Bacteria use chemical reactions, not light, to produce energy. This process is called chemosynthesis. Entire ecosystems exist around these vents. Worms, crabs, microbes, all living in total darkness, all powered by chemistry. This discovery changed biology forever. It proved that life does not need sunlight. It needs energy, water, and chemistry. Now imagine a rogue planet with a subsurface ocean and hydrothermal activity. The ingredients would be there: liquid water, heat, minerals, chemical gradients, time. From a scientific perspective, this is enough to make life at least possible. Life on such a planet would be very different from life on Earth's surface. It would likely be microbial, simple, slow-growing. It might exist around cracks in the ocean floor where heat and minerals emerge. There would be no plants, no eyes, no colours, no concept of day or night. Life would be adapted to constant conditions, stable temperatures, and eternal darkness. But life does not care about beauty or sunlight. It cares about survival. Another advantage of underground oceans is protection. A thick layer of ice shields the ocean from radiation, cosmic rays, and impacts. On a rogue planet drifting through space, this protection could be crucial. While the surface is exposed to harsh conditions, the ocean below remains stable. This stability could last for billions of years. On Earth, mass extinctions often occur because of changes on the surface, climate shifts, asteroid impacts, volcanic eruptions. Underground oceans on rogue planets would be isolated from many of these threats. In some ways, they might be safer places for life than planetary surfaces. However, there are still many uncertainties. One major question is energy supply. Internal heat and radioactive decay provide energy. But how much? Is it enough to support complex chemistry over long timescales? Does it remain steady, or does it fade too quickly? Another question is chemistry. Life as we know it relies on certain elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. These elements must be present and available in the ocean. We do not yet know how common such chemistry is in rogue planets. Some may be rich in these elements, others may not. There is also the issue of isolation. A rogue planet's underground ocean is completely sealed off from the outside universe. No new material falls in, no sunlight drives cycles, everything happens slowly. This could limit evolution. Life may remain simple, or it may never begin at all. So while the possibility is exciting, scientists remain cautious. They do not claim that life exists on rogue planets. They claim that it could exist, and that distinction matters. What rogue planets do is expand the definition of habitability. They show us that life-friendly environments may exist far beyond the narrow zone around stars. They force us to consider the galaxy as a much more diverse place. If life can exist in underground oceans on starless planets, then the number of potential habitats in the universe increases dramatically. The galaxy may contain countless hidden oceans, each one sealed beneath ice, drifting silently through space. These worlds would never be detected by traditional planet hunting methods. They would not dim starlight, they would not reflect sunlight, they would be invisible, yet they could be alive. This idea is both humbling and unsettling. It means that life could be common but hidden. It could be widespread but silent. Entire biospheres could exist without ever announcing themselves to the cosmos. It also means that our search for life must be creative. We cannot only look for Earth-like planets around stars. We must think deeper, literally. Underground oceans represent one of the most powerful arguments that planets without stars are not meaningless. They are not just frozen leftovers. They are potential laboratories for life. In the end, the question is not whether life needs a star. The question is whether life needs energy, stability, and time. And in the dark depths of rogue planets, those conditions may quietly exist, waiting, unseen, for science to one day uncover them. Detecting a planet is hard even when it orbits a bright star. Detecting a planet with no star at all is one of the hardest challenges in modern astronomy. These worlds do not shine. They do not reflect sunlight. They do not create regular signals. They move silently through space like shadows. So how do scientists find something that is almost completely invisible? The answer is clever physics, patience, and a deep understanding of gravity. To understand how starless planets are detected, we first need to understand why they are so difficult to observe in the first place. A normal planet is usually discovered by watching its star. When a planet orbits a star, it leaves clues. It pulls the star slightly, causing a wobble. It may pass in front of the star, causing a small dip in brightness. Astronomers do not usually see the planet itself. They see its effect on the star. A rogue planet has no star, no wobble, no dimming, no repeating orbit. It gives us nothing obvious to track. It does not glow like a star. It reflects almost no light. Most rogue planets are extremely cold, so they emit very little heat. Against the dark background of space, they are practically invisible. For a long time, this meant that rogue planets were undetectable. Then scientists found a way to let gravity do the work. This brings us to the most important tool for finding starless planets: gravitational microlensing. Gravitational microlensing sounds complex, but the basic idea is simple. Gravity bends space. This is one of the key ideas of Einstein's theory of general relativity. Massive objects do not just pull on other objects, they bend the space around them. When light passes through this bent space, its path curves. Imagine space like a stretched fabric. Put a heavy ball on it, and the fabric dips. Roll a marble nearby, and it curves toward the dip. Light behaves the same way. Now imagine a distant star shining toward Earth. If a massive object passes between that star and us, its gravity bends the star's light. For a short time, the star appears brighter. This brightening is called a microlensing event. The object doing the lensing does not need to emit light. It only needs mass. A star can cause microlensing. So can a planet. When a rogue planet passes in front of a distant star, its gravity briefly magnifies the star's light. The brightening lasts from a few hours to a few days, depending on the planet's mass and speed. Then it ends. The planet moves on. The star returns to normal. The signal is gone forever. This is why microlensing is both powerful and frustrating. It allows astronomers to detect objects that emit no light at all. But each detection is a one-time event. There is no second chance to observe the same planet again. Astronomers monitor millions of stars at once, especially in dense regions of the galaxy like the galactic center. They watch patiently, waiting for rare microlensing events to occur. When one happens, computers flag it. Scientists analyze the shape and duration of the brightening. From this, they can estimate the mass of the object that caused it. If the mass matches that of a planet and no star is detected nearby, the conclusion is clear. A rogue planet has passed by. This is how the first starless planets were discovered. But microlensing has limitations. It does not tell us much about the planet itself. We cannot see its surface. We cannot study its atmosphere. We often cannot even determine its exact distance. Microlensing tells us that the planet exists. That is all. Another reason rogue planets are hard to observe is speed. Rogue planets move quickly across the sky. They do not follow predictable orbits around visible objects. This makes long-term observation extremely difficult. Even if a rogue planet passes relatively close to Earth, it may still be invisible unless it happens to align perfectly with a background star. There is also the issue of rarity. Microlensing events are rare because they require precise alignment between Earth, a distant star, and a rogue planet. Most rogue planets drift through space without ever crossing our line of sight to a background star. This means astronomers must watch enormous numbers of stars continuously to catch a few events. This is where modern telescopes and space missions become essential. Ground-based surveys like OGLE and MOA have been monitoring millions of stars for years, looking for microlensing events. These projects laid the foundation for rogue planet detection. But Earth-based observations have limits. The atmosphere blurs images. Weather interrupts observations. The night sky is not always available. This is why space-based telescopes are so important. The upcoming Nancy Grace Roman Space Telescope, for example, is designed to conduct large microlensing surveys from space. Without atmospheric interference, it can monitor stars with incredible precision. It is expected to detect thousands of rogue planets. Infrared telescopes also play a role. Young or massive rogue planets may still emit heat from their formation. Infrared telescopes can sometimes detect this faint glow. This method works best for nearby rogue planets that are still relatively warm. However, this approach only finds a small fraction of rogue planets. Most are too cold and too distant to detect this way. There is also direct imaging, which involves taking pictures of planets themselves. This method is extremely difficult, even for planets around stars. For rogue planets, it is nearly impossible unless they are very young, very massive, and very close. So far, only a few candidate rogue planets have been detected through direct imaging. Another promising approach is studying stellar motion. As rogue planets pass near stars, their gravity can slightly alter the star's paths. Over long timescales, careful measurements may reveal these subtle effects. This method is still developing and requires extremely precise data. Despite all these tools, our view of rogue planets is incomplete. We are biased toward finding certain types of rogue planets. Large ones, fast-moving ones, ones that pass through dense star fields. Countless others remain undetected. This is a key limitation of current technology. We know rogue planets exist. We know they are common, but we are seeing only the tip of the iceberg. We cannot yet map their distribution across the galaxy. We cannot study their chemistry. We cannot tell how many have moons, atmospheres, or internal oceans. Most rogue planets will remain invisible for the foreseeable future. This is not a failure of science. It is a reminder of scale. The galaxy is vast. Rogue planets are dark. Our tools are still young. Yet even with these limitations, the fact that we can detect starless planets at all is remarkable. A century ago, the idea would have sounded impossible. Today, it is a growing field of research. As technology improves, our methods will become more sensitive. Future telescopes may detect heat signatures from colder planets. New techniques may reveal gravitational effects we cannot yet measure. One day, we may even detect signs of underground oceans or internal activity indirectly. For now, scientists work with shadows and brief flashes of light. They piece together evidence from fleeting events. They build statistics from rare alignments. And from this limited data, a profound picture emerges. The galaxy is not just a collection of stars with planets around them. It is also filled with wandering worlds, moving unseen between the stars. We cannot see most of them. We cannot touch them. But we know they are there. And the fact that we can detect planets with no stars at all is one of the quiet triumphs of modern astronomy. When astronomers first confirmed the existence of starless planets, the discovery itself was shocking. But what truly unsettled the scientific world was not just that these worlds exist. It was the question that followed almost immediately. How many of them are out there? At first, scientists assumed rogue planets must be rare. Strange exceptions, cosmic accidents, a few unlucky worlds kicked out of their homes. That assumption felt safe. It protected the old idea that stars dominate the universe and planets are mostly loyal companions. But as more data arrived, that comfort began to disappear. The numbers did not stay small. They grew. And with every new estimate, the universe became far more crowded than anyone had imagined. The earliest estimates of starless planets came from gravitational microlensing surveys. These surveys monitored millions of stars, waiting for brief flashes of light caused by unseen objects passing in front of them. When scientists analysed the frequency and duration of these events, they began to notice something unexpected. Too many of the lensing signals were caused by objects with planetary mass, and too few stars were responsible. In other words, something small and massive was passing through the galaxy in large numbers, without shining. When researchers converted these observations into population estimates, the results were astonishing. Some studies suggested that rogue planets could be as common as stars in the Milky Way. Others suggested they might be even more numerous. That meant one thing. For every star you see in the night sky, there could be one or more invisible planets drifting in the darkness between them. To understand why this is possible, we need to think about how stars and planets form on a galactic scale. Stars form in clusters, rarely alone. In these clusters, planetary systems are born in crowded environments. Gravitational interactions are frequent. Young systems are unstable. Planets migrate, orbits cross. Ejections happen naturally. If even a small fraction of planets are ejected from each system, the numbers add up quickly. Consider this: if the average star system forms several planets, and even one of those planets is lost during early chaos, the galaxy gains a rogue planet. Multiply that by hundreds of billions of stars, and the population of starless planets becomes enormous. This is not speculation. Computer simulations of planetary system formation consistently show that ejection is common. In some models, more planets are lost than retained. Now add another factor. Not all rogue planets need to come from ejection. As discussed earlier, some may form independently, directly from collapsing gas clouds that never ignite into stars. Even if this process is rare, it adds another source of starless worlds. So, scientists began to ask a bold question. What if rogue planets are not a minority at all? What if they are one of the dominant forms of planetary mass in the galaxy? Some studies now suggest that the Milky Way may contain hundreds of billions to trillions of rogue planets. This number is difficult to grasp. Our galaxy is estimated to contain around 100 to 400 billion stars. If rogue planets match or exceed that number, then planets without stars could be one of the most common objects in the galaxy, and yet we barely see them. This leads to an important realization. The visible universe is only a small part of what exists. We tend to think of the galaxy as a collection of stars with planets neatly orbiting them, but this picture is incomplete. Between the stars lies a hidden population of worlds that do not shine, do not announce themselves, and do not fit neatly into our mental maps. The Milky Way is not empty space dotted with stars. It is a crowded environment filled with invisible mass. This changes how we think about galaxy structure. Stars dominate what we see, but they may not dominate what exists. Rogue planets add mass to the galaxy. Not enough to explain dark matter, but enough to matter on local scales. They influence gravity. They affect stellar motions in subtle ways. They contribute to the galaxy's overall mass distribution. In dense regions like the galactic center or star-forming clusters, rogue planets may be especially abundant. These regions are chaotic. Stars pass close to each other. Systems are disrupted. Planets are scattered. In quieter regions, rogue planets still exist, drifting slowly through interstellar space, remnants of ancient chaos. This means that the space between stars is not empty. It is filled with worlds. Most of them are cold, dark, silent, but they are there. This also changes how we think about encounters. The chances of a rogue planet passing near a star, or even being captured by one, are small, but not zero. Over billions of years, rare events become inevitable. Some stars may capture rogue planets, creating systems with unusual orbits and histories. Some planets in known systems may not have formed there at all. They may be immigrants from elsewhere in the galaxy. This adds a new layer of complexity to planetary science. Planets are not just born and fixed. They move, they travel, they can be exchanged. The galaxy becomes a dynamic ecosystem, not a static map. Another implication is philosophical. When we look up at the night sky, we see stars and imagine emptiness between them. But if rogue planets are common, then the darkness is full. The universe is not sparse, it is crowded beyond our senses. There could be a rogue planet passing within a few light years of Earth right now, completely invisible, known only by its gravitational presence. This idea can feel unsettling or awe-inspiring. It reminds us that our perception is limited. That reality is far richer than what light reveals. There is Also, an implication for the search for life. If rogue planets are common, and if even a small fraction of them host underground oceans, then the number of potential habitats in the galaxy increases dramatically. Life may not be rare because planets are rare. It may be rare because life is difficult. Or it may not be rare at all. We simply do not know yet. What we do know is that stars are no longer the only places to look. Habitability is no longer confined to a narrow zone around suns. It may extend into the dark spaces between them. This forces science to expand its imagination. The idea of a universe more crowded than we imagined is not just about numbers, it is about perspective. For centuries, astronomy was the study of light, what shines, what glows, what can be seen. Rogue planets challenge that tradition. They demand that we study mass, gravity, and absence. They remind us that existence does not require visibility. The Milky Way may be filled with worlds that will never be photographed, never be visited, and never be named. Worlds that drift silently for billions of years, carrying their own histories, their own internal processes, and perhaps even their own forms of life. So when we ask how many starless planets are out there, the most honest answer is this: more than we once thought, more than we can currently detect, and enough to fundamentally change how we understand the galaxy. The universe is not just a place of stars and light, it is a place of darkness filled with worlds. As strange as starless planets may seem, there is one question that brings the idea uncomfortably close to home. Could Earth ever become one of them? This is not just a science fiction question, it is a powerful thought experiment that helps us understand what stars truly mean to planets, and how fragile our sense of stability really is. By imagining Earth without the sun, we can explore what happens when a world loses its star and whether life can hold on in the darkness. Let us begin with the most dramatic assumption. The sun disappears, not explodes, not slowly fades, simply vanishes. This scenario is unrealistic in real astrophysics, but it is useful because it isolates one variable. It lets us see how deeply Earth depends on the sun and what happens when that support is removed instantly. The first thing to understand is this: if the sun disappeared, gravity would change immediately. Earth does not orbit the sun because of habit or momentum alone. It orbits because the sun's gravity holds it in a curved path. Remove the sun, and Earth would stop orbiting instantly. It would continue moving in a straight line at its current speed, drifting off into space. Earth would become a rogue planet. The Moon, however, would still orbit Earth. Satellites would still orbit Earth. Earth would carry its small system with it as it left the solar system behind. But motion is not the most immediate danger. Darkness is. About 8 minutes after the sun vanished, its light would stop reaching Earth. That is how long sunlight takes to travel across space to us. There would be no warning. One moment, daylight. The next, night. Permanent night. The sky would go black. Not twilight, not sunset, full darkness. The stars would appear instantly, even during what was once daytime. Temperatures would begin to fall almost immediately. Within hours, Earth's surface would start cooling rapidly. The atmosphere would begin losing heat to space. Without incoming solar energy, Earth would radiate its warmth away like a hot object placed in a freezer. Within days, surface temperatures would drop below freezing everywhere on the planet. Within weeks, the oceans would begin to freeze. But this freezing would not be uniform. The first layers of ocean water would turn to ice at the surface, forming a thick, insulating shell. Ice is a poor conductor of heat, which means it slows down further cooling. This detail is critical. It means Earth would not instantly become a solid ice ball. Over the first year, average surface temperatures could drop to around -50 to -70 degrees Celsius. Storms would cease, winds would weaken, weather would stop behaving the way we know it, plants would die quickly. Photosynthesis depends entirely on sunlight. Without it, plants would exhaust their energy reserves and die within weeks. Crops would fail almost immediately. Forests would become lifeless. Animals that depend on plants would follow soon after. Within months, most surface ecosystems would collapse. But life on Earth is not limited to the surface. As time passed, the oceans would continue freezing from the top down. After 1 year, ice could be several meters thick. After 10 years, tens of meters. After centuries, possibly hundreds of meters. But beneath that ice, liquid water could still exist. Earth has internal heat. Radioactive decay inside the planet would continue. The core would remain hot. Heat would still flow upward, slowly warming the ocean from below. This internal heat is why Earth would not freeze solid immediately, or perhaps ever completely. After about 1,000 years, Earth's surface temperature could fall below -100 degrees Celsius. The atmosphere would begin to collapse. Gases like carbon dioxide and oxygen could freeze and fall as snow. Eventually, much of the atmosphere would settle onto the surface as ice. The sky would become thin, silent, still. Yet deep below, the story would be different. At the bottom of the oceans, near hydrothermal vents, heat from Earth's interior would continue to drive chemical reactions. These environments already exist today. They are home to organisms that do not depend on sunlight at all. Life near these vents uses chemical energy released from the planet itself. In a starless Earth, these places would become the last refuges of life. Microbial life could survive for a very long time, possibly millions or even billions of years, as long as Earth's interior remained. Warm enough to support liquid water and chemistry, life could persist. Complex life, however, would struggle. Large animals require a lot of energy. Food chains based on chemosynthesis are much smaller and less productive than those based on sunlight. Over time, Earth's biosphere would simplify. Life would retreat inward, downward, into darkness. Eventually, even Earth's internal heat would fade. Radioactive elements decay slowly, but they do decay. Over billions of years, the planet would cool further. Oceans would freeze deeper. Liquid water would shrink. At that point, Earth would resemble the most extreme rogue planets we imagine today. A frozen shell surrounding a slowly cooling interior. But this timeline is not measured in days or years. It is measured in geological time. From a human perspective, the loss of the sun would mean near immediate extinction. Civilization would collapse within days. Most life would be gone within years. From a planetary perspective, Earth would endure. It would remain intact. It would carry its mass, its gravity, its moons, and its history through space. It would drift silently through the galaxy, another dark world among many. This thought experiment teaches us something profound. Stars are essential for surface life as we know it. They provide light, warmth, and energy. They shape climate and drive ecosystems. But they are not required for a planet to exist, and they may not be required for life to exist either. Earth without the sun would be hostile, dark, frozen, but not immediately dead. Life would not vanish in an instant. It would adapt, retreat, and survive where it could. This is exactly what scientists imagine might happen on rogue planets. A planet does not stop being a planet when it loses its star. A biosphere does not vanish instantly when light disappears. Instead, everything slows down, contracts, simplifies. The thought experiment also reminds us of how lucky we are. Earth's position near a stable star at just the right distance is what allows complex life to thrive on the surface. This is rare, fragile, temporary. The sun will not disappear suddenly, but one day, billions of years from now, it will change, it will expand, it will alter Earth's environment, and eventually it will fade. Starless planets are not just distant curiosities. They are possible futures for worlds like ours. By imagining Earth as a rogue planet, we understand both the limits and the resilience of life. We see how dependent we are on light and how stubborn life can be in its absence. It is a humbling reminder. Our world feels permanent because we live inside a moment of stability. But the universe is not static. Stars are born, stars die, planets are ejected, worlds drift. Earth is not immune to cosmic change. And yet, even in the darkest scenario, life may find a way to hold on. That possibility is what makes the idea of starless planets not just frightening, but deeply fascinating. Rogue planets do more than add a strange new category to astronomy. They force us to rethink some of the deepest assumptions we have ever made about the universe. For centuries, our understanding of space was built around light, order, and stable systems. Stars were the anchors, planets were companions, everything had a place. Rogue planets break that picture. They are not rare mistakes or cosmic leftovers. They are teachers. And what they teach us reaches far beyond the question of planets without stars. The first and most important lesson is this: many of the rules we thought were universal are actually local habits. For most of human history, astronomy was based on what we could see. Stars shine, planets reflect light. So naturally, we define the universe in terms of light. Anything dark was ignored or assumed not to matter. Rogue planets challenge this bias directly. They show us that visibility is not the same as existence. The universe is not built only from what shines. It is built from mass, gravity, motion, and time. Light is just one way of revealing these things, not the foundation of reality itself. This challenges one of the oldest assumptions in astronomy, that planets must orbit stars. This idea was never written into the laws of physics. It was inferred from observation. We saw planets orbiting the sun, so we assumed that was the definition. Rogue planets expose the flaw in that thinking. They show us that orbiting a star is common, but not essential. A planet is defined by what it is, not by what it circles. Once that idea sinks in, astronomy becomes far more flexible and far more honest. This shift mirrors other revolutions in science. Earth was once thought to be the center of the universe. Then the sun took that place. Now even stars are losing their special status as the sole organizers of planetary existence. The universe keeps reminding us that our preferred structures are not laws, they are conveniences. Rogue planets also redefine what it means for a world to be habitable. For decades, habitability was tied almost entirely to stars. The concept of the habitable zone became central. A narrow ring around a star where liquid water could exist on a planet's surface. Too close, and water boils away. Too far, and it freezes. This framework made sense. It was simple. It worked for Earth. But rogue planets expose its limits. They show us that habitability is not only about distance from a star, it is about energy, chemistry, and stability. Internal heat, chemical reactions, time. A planet does not need sunlight if it has another reliable energy source. Underground oceans powered by radioactive decay or tidal heating can remain liquid for billions of years. Life, if it exists, does not need to see a sunrise. This forces a profound rethinking of the search for life. Life may not be rare because habitable zones are rare. It may be rare because life itself is rare. Or it may not be rare at all, but hidden in places we have barely considered. Rogue. Planets expand the map of possible life-bearing worlds dramatically. The galaxy is no longer a collection of narrow habitable rings around stars. It becomes a three-dimensional network of potential habitats, many of them buried beneath ice and darkness. This does not mean life is everywhere, but it means our previous search space was far too small. Another lesson rogue planets teach us is about chaos and balance. We like to think of planetary systems as stable machines. Once formed, everything settles into predictable paths, but rogue planets reveal how temporary that stability really is. Planetary systems are born chaotic. Gravity pulls in many directions. Orbits shift. Worlds collide. Some survive, some do not. Rogue planets are evidence of this process. They are not anomalies. They are records of instability. Each one tells a story of a system that changed, broke, or rearranged itself. This helps scientists understand the true nature of planetary evolution. Systems do not simply form and remain fixed. They evolve, they lose members, they gain new ones. Over time, they become quieter, but they are never perfectly still. This perspective also helps explain why planetary systems look so different from one another. Why some have hot, giant planets hugging their stars. Why others have tilted orbits. Why some seem oddly incomplete. Rogue planets are missing pieces. They show us that what we see today is not the full story. Many worlds have already been lost. There is also a deeper lesson about balance. Chaos does not mean randomness. It means sensitivity. Small differences early on can lead to very different outcomes later. A slight change in orbit, a close stellar pass, a small shift in mass. Rogue planets are reminders that the universe is shaped by these subtle interactions, playing out over immense timescales. They teach us humility. Another reason lonely planets matter scientifically is that they allow us to study planetary physics in isolation. Planets around stars are constantly influenced by radiation, stellar winds, and tidal forces. These effects complicate analysis. It is often difficult to separate what a planet is doing on its own from what its star is doing to it. Rogue planets remove that complication. They are natural laboratories for studying planetary interiors, cooling rates, atmospheric loss, and long-term evolution without stellar influence. They show us what planets become when external energy sources are removed. This helps scientists understand not just rogue planets, but all planets. For example, by studying how quickly rogue planets cool, we can refine models of planetary heat retention. By studying their atmospheres, if detectable, we can learn how atmospheres behave without sunlight. By studying their mass distribution, we can test theories of planet formation and ejection. In this sense, rogue planets are not peripheral objects. They are central to understanding planetary science as a whole. They also help bridge gaps between fields. Rogue planets sit at the boundary between astronomy, planetary science, geology, and astrobiology. They force collaboration. They demand new methods. They inspire new questions. They also push technology forward. Detecting something that does not shine requires extreme precision and creativity. Techniques developed for rogue planet detection improve our ability to study dark matter, distant stars, and subtle gravitational effects. So even when rogue planets are not the main target, the effort to find them advances science broadly. There is also a philosophical lesson in all of this. Rogue planets remind us that loneliness does not equal insignificance. For a long time, importance in astronomy was linked to brightness, the brightest stars, the most energetic events, the most violent explosions. Rogue planets are the opposite: quiet, dark, cold, and yet they may outnumber stars. They may host hidden oceans. They may preserve ancient histories untouched for billions of years. They matter not because they are dramatic, but because they are common. This changes how we think about the universe. It becomes less of a stage for spectacular events and more of a vast, quiet system where slow processes shape reality over time. Lonely planets also change how we think about our own place in space. Earth feels special because it is warm and bright and alive. And it is special, but it is also temporary. The conditions that make Earth what it is will not last forever. Rogue planets are reminders of what remains when light fades. They are the long-term state of many worlds. By studying them, we gain perspective. We see that the universe is not designed for comfort or permanence. It is designed for change. And yet, within that change, structure emerges. Planets persist. Life may persist. Complexity may arise even in darkness. That is perhaps the most powerful lesson rogue planets teach us. The universe is more resilient, more flexible, and more surprising than our old rules allowed. It does not need stars everywhere to create worlds. It does not need light everywhere to create possibility. Rogue planets matter because they reveal a universe that is not neatly organized around suns, but filled with countless worlds, each following its own quiet path through the dark. And in that darkness, science continues to find meaning. When we look up at the night sky, our eyes are drawn to the brightest things: stars, nebulae, galaxies glowing across unimaginable distances. Light has always guided our curiosity. It feels natural to believe that light is where the story is, and darkness is where nothing happens. But rogue planets quietly ask us to reconsider that belief. They tell us that the universe does not revolve only around stars. Between every shining sun, between every glowing system, there are worlds drifting silently through space. Worlds with no sunrise, no warmth from above, no visible sign that they are even there. And yet, they exist, they move. They carry mass, history, and possibility. These planets are not broken. They are not unfinished. They are not mistakes. They are simply different. For a long time, we defined importance in the universe by brightness. Stars mattered because they shone. Planets mattered because they reflected that light. Anything dark was treated as empty space. But rogue planets reveal how incomplete that picture is. Darkness is not absence. Darkness is just unseen presence. A starless planet drifting through the galaxy may look lifeless from a distance, but beneath its frozen surface, heat may still flow. Chemistry may still work. Time may still shape it, slowly and patiently. Some may hide oceans sealed under ice. Some may preserve ancient scars from violent beginnings. Some may carry moons, atmospheres, even internal storms. They're quiet worlds, but they're not simple ones. There is something deeply humbling about that idea. We often imagine the universe as a place built for spectacle. Explosions, collisions, bright endings and dramatic beginnings. Rogue planets remind us that most of the universe is not loud, it is slow, it is cold, it is patient. Worlds can exist for billions of years without ever announcing themselves. They do not need light to justify their existence. They do not need an audience. They simply are. This realization changes how we see our own planet. Earth feels special because it is alive, warm, and bright, and it is. But it is also temporary. Its warmth depends on a star that will one day change. Its surface life depends on light that will not last forever. In cosmic time, Earth's current state is a brief moment of balance. Rogue planets show us what comes before and what comes after. They are reminders that planets endure long after stars stop defining them, that worlds can persist even when light disappears. That existence does not end when conditions change, it adapts. This is not a sad thought, it is a grounding one. It tells us that the universe is not fragile. It is resilient in ways we are only beginning to understand. There is also a quiet beauty in the idea of these lonely worlds. Imagine a planet drifting through interstellar space, its surface frozen solid, its sky permanently black. No dawn, no dusk, only distant stars slowly shifting as the planet moves through the galaxy. Beneath kilometers of ice, a hidden ocean remains liquid, warmed by heat from the planet's heart. Chemical reactions unfold, molecules interact. Perhaps life exists there, unaware of stars, unaware of light, unaware of the vast universe above. That possibility does not need to be proven to matter. It expands our sense of what is possible. For centuries, humanity believed that life and meaning were tied to specific conditions, to sunlight, to warmth, to familiar environments. Rogue planets challenge that comfort. They ask us to accept that reality may be far stranger and far richer than our preferences allow. They teach us that habitability is not a narrow ring around a star, it is a spectrum, a range of environments shaped by energy, chemistry, and time. They teach us that chaos and loss are not failures of the universe. They are creative forces. The same chaos that ejects a planet from its star also creates diversity, movement, and unexpected outcomes. They teach us that loneliness does not equal insignificance. A planet wandering alone through space may never host civilizations or oceans of life. Or it may host something subtle and enduring that never needs light at all. Either way, its existence matters because it is part of the universe's story. And perhaps that is the deepest lesson of all. The universe does not exist for us. It does not arrange itself to match our expectations or definitions. It does not prioritize what we find comfortable or beautiful. It explores all possibilities. Some worlds are born in fire, some worlds are shaped by light, and some worlds grow quietly in darkness. As we continue to explore space, our greatest discoveries may not always be the brightest ones. They may be the faint signals, the brief gravitational whispers, the moments when something invisible reveals itself just enough to remind us how much we do not know. Rogue planets sit at the edge of our awareness. They're easy to ignore, hard to detect, difficult to study, but they carry an important message. The universe is bigger than what we see, richer than what we expect, and humbler than what we imagine. In the end, worlds without light invite us to slow down our thinking, to listen instead of stare, to accept that mystery is not a problem to be solved, but a condition to be respected. There are planets drifting through the galaxy right now that will never know a sunrise. They will never glow in telescope images. They will never become destinations. And yet, they are as real as any world warmed by a star. They remind us that existence does not require attention, that meaning does not depend on brightness, and that even in the deepest darkness of space, the universe is still quietly full of worlds. And perhaps that is where the greatest wonder truly lives.